reminders. You guys remember your we had a writing assignment, so that should have been done on Monday, but if you didn't get it done, still just get it done. We're going to come back to that question a couple times throughout the semester, so it's really interesting to get your take on it at the beginning of the class. If you didn't, make sure you fill out the expectations. So I like that to be anonymous. I'm not collecting your information there. So just so you feel free to say what you want. But will take a look at those and address them on Monday. Okay. The workbook. A lot of you have been asking if, what if I don't have my workbook? What if I just ordered it? That's fine. Don't worry. For the first few weeks, if you need it, I will post the sheet in Canvas, but I won't do that the whole semester. I actually just realized that I lent my workbook out and I don't even have mine either. So don't worry, we're not using it today. And then the online text, like I said, this is the first semester we're using that online text. I know there's, depending on how you're looking at it, like I've looked at it on an iPad, I've looked at it on a Mac computer, and I've also looked at it on a PC. And so I have, it's the way the table of contents looks different in each one. So I'm going to try to put in the page numbers. So for the beginning part, we're starting at the beginning of chapter 5 in that online text. It's chapter 13 if you're using Leninger. But again, if you're using something else, you can always just kind of go to a table of contents and just kind of look for the topics. Okay. And it's like page 410 to 429 in that online text. Okay. And anyone using Leninger, it should match up pretty nicely. I'm going to share my other screen. Don't want to share it. Yeah, so I'll share this. I'll share my screen with you guys real quick. Okay. So under week 1, this, you guys can't see this yet. Let me see. Let me go to state of view. But under week 1, I did make some slides available. So I put the Leninger slides. So these are the slides from the Leninger book, the whole chapter 13 slides, if you want to look at those. And then I have my edited slides. And so if you have access to those. I put these other 2 little video clips in here. These are 2 little movies I made a while ago. And they're just about some things that we don't spend a lot of time on. So I made videos about them. Today in class, we'll work on this group assignment. So whenever you see the word GA, that to me is group assignment. So we'll work on it together. And I put the due date for this today, but I put it by midnight. So again, if people don't get to it in class, they can get to it later. And I did put a class prep assignment on here. And this is due by next Monday, okay, for our next class. And I'm not looking for right or wrong answers here. I am just trying to get you guys thinking about the material, okay? And so I will put a key up for this after we turn it in, but yeah, so just to make you aware of that, there's this prep assignment for next Monday. Group assignment for today, some videos and some slides. All right, questions about any of that? Okay. All right, so then I'm actually plan on writing today, so I'm gonna use my iPad for that. So I'm gonna stop sharing here. All right, let's get started. All right. Okay, so we are starting our journey learning about metabolism. Let me get this set up. Oh, you can still see my face. Okay, interesting. Okay. And so, as you guys heard in that video that we saw on Monday, we can think of metabolism as a sum of all the chemical transformations that take place in a cell or organism, okay? So sum. Okay. All right, and so again, as we saw in the video on Monday, we talked about catabolism, okay? And this is where we'll focus a lot of our time is on catabolism. And this is the degradative phase, okay? And so usually we can, reactions that fall under catabolism, we call them catabolic, okay? And usually here they're going, we're going from larger molecules to smaller. These reactions are oxidative. Now, of course, we'll talk a lot about redox, and you guys should know that whenever you have a redox reaction, you know, you can't have an oxidation without a reduction. So if we're saying they're oxidative, it means the substrate is getting oxidized. Of course, something else has to be getting reduced, and we'll look at that, okay? And in these cases, ATP captures most of the energy. Okay. So on the other side is anabolism. And again, reactions that fall under these types of reactions, we call them anabolic. You guys have a really great view of my face here. It's really, you know, this is not a good angle here, but that's okay. All right, so here in anabolic reactions, we're going from smaller molecules to larger ones, okay? Oh, that works, okay. Okay. And these tend to be reductive, okay? So again, we can't have a reduction without an oxidation, but the substrates are getting reduced, and they tend to have, they require an input of energy. So energy is input. Okay, so most of the reactions we look at this semester, well, all of them are going to either be catabolic or anabolic. And again, catabolic are going to break things down, substrates are going to get oxidized, and energy is going to be released. Anabolic reactions, we're building stuff. Maybe we're taking amino acids and putting them together to like form a protein. We're reducing the substrate, and we have an input of energy required. Okay. All right. So there's a nice picture of this in Leninger. I don't have it though. And but there's a big flow of energy, okay, in our biosphere. There's a big flow of energy, right? And you guys are aware of this. We have plants that capture the sunlight, right? They capture the energy from the sun, which is amazing. They do this for us, right? And they use that energy to generate rich carbohydrates and oxygen for us, right? So plants are the autotrophs, okay? They use photosynthesis. Where animals were heterotrophs, right? And we break down those nutrients and we give off CO2, okay? So there's just this huge flow of energy between the plants, the sun, and us, okay? And I mean, obviously it gets really complicated, but there's just this huge transfer of energy taking place in the biosphere. And anytime we have like stuff to do with energy, this is governed by the laws of thermodynamics, okay? So, okay. All right. So again, you guys have probably seen this in another class. Okay. But we're going to review it briefly. All right, first law. You guys probably remember is total energy remains constant, right? It's the conservation of energy. So this is important, right? Because the energy is not going to get lost somewhere, right? It changes forms, but it's not created, it's not destroyed. Okay, so first law of thermodynamics is energy is conserved. Okay. Now the second law of thermodynamics is that the universe always tends towards increasing disorder. Right? Or entropy, you guys have learned. Okay. All right. Okay. So okay. And then you have the third law of thermodynamics. Oh, I'm sorry, but we don't need to talk about that. Okay. Let's go. Do you guys have any questions so far? Pretty straightforward. Okay. Again, we'll review a lot of stuff here. So we have 3 thermodynamic quantities to describe these energy changes, right? We need these to describe our flow of energy here. And so we have our, let's write that down. Again, you guys have seen these all before. We have Gibbs free energy. Which, you know, we use a capital G. Remember, Gibbs free energy tells us the amount of energy that's capable of doing work. Okay. So, yeah. Okay. Then we have, oh, and with Gibbs free energy, remember, we call it exergonic if there's a release of free energy. So if energy is released, then we have, it's called exergonic, and we have a negative delta G. So a negative delta G. Okay. And it's the opposite. If we have a positive delta G, remember, then it gains energy, or energy is input into the system. Okay. All right. So that's one. A second one is enthalpy. Okay. Remember, this is our heat content. This tells us, it gives us an idea of how many, like the number and the kinds of chemical bonds in our reactants and in our products, right? Do we have a really stable bond, a really strong bond, or is it unstable? Okay. Remember the terms we use here, if we have like a negative delta H, you've heard exothermic, right? And there's a release of heat. Okay. And then the opposite, again, a positive delta H is considered endothermic. Okay. And we can think of that not releasing heat, but actually taking up heat from the surroundings. Okay. So that's our second quantity. All right. And we have 3 of them. Our last one is entropy.
Professor Lawrence,
Yes.
so the exothermic and endothermic is just based on how stable the bonds are?
Yes. Well, it depends, right? Because and we'll look at like an energy diagram, but it's going to depend on, right, like what types of bonds are you starting with, like are present in your reactants, and then what kind of bonds are you ending up with, right? Do you end up with a more stable product, or do you end up with a less stable product?
Okay.
Okay. So entropy, we use S to describe that. And remember, this is a quantitative value for the randomness or disorder in a system, okay? So quantitative. Okay. Okay. So we know that these 3 quantities, our Gibbs free energy, our enthalpy, and our entropy, they're related by an equation you guys hopefully have seen several times, but I will remind you of this. Okay. And so these are how these 3 quantities are related. And T here is the absolute temperature. Okay. Delta G here, we can try some tools. Delta G gives us the idea of the spontaneity of a reaction. Okay. So if a reaction is spontaneous, then delta G is always negative. Okay. All right. Now we said, remember, this is cool because I can go back to there. Okay. Remember in our second law that the universe is always tending towards increasing disorder, right? Or increasing entropy. So that was our second law. I'll come back to this other screen. Oops. Okay. But if you guys look at us like living organisms, we're highly, highly organized, right? And so I want you to think about that, right? And we'll take time to do that group assignment later, but do organisms disobey the second law of thermodynamics, right? We are organized into like our organelles, you know, that we're organized with our cells. We're a highly ordered species here. Okay. So we'll look a little bit more at that a little bit later. Okay. All right. So as humans, we have to operate at a constant temperature and pressure, right? Most living organisms do. If in chemistry, a lot of times in lab, right, you can turn up the heat on reaction, you can put it under high pressure, you can add some nasty solvents, right, to help reactions go. But in nice biological systems, we can't do all those stuff, all the stuff we might do in lab, we can't really do to us, right? We have to operate at this constant temperature and constant pressure, okay? So that's one thing to take into consideration. Another thing is that reacting systems, when there is a reaction, remember they tend to react until equilibrium is reached. Okay. So again, that's probably stuff you've heard a lot up to this point. And remember, equilibrium just means that the rate of the forward and reverse reaction are equal, right? There's no net change, okay, in the system. Okay, so let's talk a little bit about equilibrium constants. Well, you know what? Before we go into equilibrium constants, that's where we're going next. But I'm actually going to go ahead and put you guys in groups for just a couple minutes. And I want you to talk about that idea of, do organisms disobey the second law of thermodynamics? Okay. So let me see here. put you guys in breakout rooms. It's going to be pretty quick. Let me see. And remember, the question is just, do organisms disobey the second law of thermodynamics? Okay. Okay, so you guys should all be back now. And let's see. Okay, and this is part of your group assignment. So it's in that Canvas page. So if you want to be typing in there while you are in your group breakout rooms, that's fine. So, but again, that's due today at midnight. So that group assignment, which was the question you worked on in your groups right now.
Dr.
Okay.
Morris, sorry, really quick question, actually. That group assignment, are we all turning in like individual, or is it like we're breakout room number, whatever, and then like it's just one with all the names?
You're turning in individually.
Cool.
You
Okay.
could work on it together, right?
Okay.
You could have the same exact answer, but yeah, you want to turn it in individually.
Okay.
And then
this isn't like the FAT with the walking and running one. Like, you would want us to use our resources and try to make a well-rounded answer, or do you want us just going off the top of our head?
oh, I just want you to, whatever you come up with in your group. I don't expect you to.
Oh,
this
okay.
shouldn't. Yeah. Yeah. You don't have to do a lot of research on it. And again, there's no right or wrong answer with the group assignments. It's just again a way for you guys to kind of take in all the stuff I just talked about, right? And kind of use your own vocabulary around the topics, and then articulate your own ideas.
Got it. Okay, sounds good.
And then you don't have to hear me talk for an hour straight. Okay. Research shows that doesn't work so well. Okay. Okay, so we were talking about our thermodynamic quantities. And so we're going to be looking at Gibbs free energy, but I want us to also be aware of equilibrium and equilibrium constants, because this is another mechanism used by cells to help drive a reaction forward. Okay, so one way reactions are driven forward are when we have a negative delta G, then they tend to proceed as written in the forward direction. Okay, and we'll talk more about this, but another kind of driving force here is equilibrium. Okay, and so let's see. Okay, all right. So remember, our equilibrium constant is KEQ. Oops, gotta change my thing. Right, in KEQ, we usually write like the concentration of all the products raised to their coefficients. Okay, so this is from some generic reaction that would look like this. Okay. All right, so our KEQ is our equilibrium constant. Remember, a system wants to reach equilibrium, so this is a driving force, okay? And we can actually express this in terms of delta G, okay? So because this can be a driving force as a source of free energy, okay? So real quick, I wanna make sure we understand some definitions. When we see like delta G, and we have a little knot, a little circle up there in the upper right-hand corner, remember that's called the standard free energy. This is a constant, okay? That means we can like look up standard free energies for a reaction, Okay, we can like go look up what is the delta G naught for, you know, phosphorylating glucose. Okay, and you'll see them throughout textbooks and stuff, because there's specifically defined reaction conditions here. Okay, so it means there's like 25 degrees Celsius. There's 1 molar concentrations of, all your products and reactants. It's at 1 atm. Okay. However, this doesn't work well for biological systems. If we had like our proton concentration was at 1 molar, we would be under very acidic conditions. And we have a lot of protons in our biologic reactions. So in biochemistry and for biological reactions, we have what are called the standard transform constants. And we have it, so we have delta G naught, make sure, and then we put a little prime up there with it. Okay, and so that is called standard transformed constants. Okay, and so there's some different definitions here. For instance, our proton concentration, H plus, is going to be equal to 10 to the minus 7 molar. Okay, so we keep it at a neutral pH. You don't have to memorize these. I just want you to be aware of the difference, that there's just different concentrations and conditions for biological systems. So everything is not considered to be at 1 molar. Okay. So these conditions are incorporated into the constants. If you see something like a KEQ with a prime, that means it's taking into consideration the biological conditions. This prime right here indicates that. Okay. Or if you see a delta G not prime, again, it's taking into consideration these biological conditions. Okay. Okay, so we can relate our equilibrium constant to our Gibbs free energy. Okay, so, and you guys have seen this before. So this is review. It's minus RT natural log of KEQ. Okay. So this is one way to express, our equilibrium constant in terms of Gibbs free energy. Okay. I want to review a couple things with you guys too. I remember when I started doing this, maybe you guys have it down, but I remember I don't know why I forgot this kind of stuff, but just real quick, you guys, if you take the natural log of 1, what do you get? Do you guys know?
0.
0.
0. All right, perfect. Okay. If you take the natural log of a number that is less than 1, do you know what happens?
Get a negative.
You get a negative, yes. Okay. And if you take the natural log of a number greater than 1, you get a positive. Okay. Now, why do I say this? I think some people like to think of the reactions this way. Some people, I think, are not going to like to think of the reactions this way. I actually really like it. Okay. So a small change in delta G here, okay, a small change in delta G can equal to a large change in our KEQ, okay? Because remember, this is on like a log scale, okay? So like if our G is at 2, our KEQ is at like 100, okay? And this is also going to affect when we start, you'll see when we look at this a little bit more, that if we have a KEQ, right, that is less than 1, meaning, again, if we go back up here, okay, if it's less than 1, that means that we have less products, then we do reactants, okay? So, right, our reactants are favored, Okay, if our reactants are favored, then if we take a natural log of a number less than 1, we get a negative. And if we have a negative times this negative, we end up with a positive delta G. And remember, a positive delta G means the forward reaction is not spontaneous. Okay, so so just be aware of that relationship, okay? Because sometimes what our body's going to do, it's going to hold reactions far away from equilibrium, okay? So, and again, we're going to see different ways that cells can do this, but the reason it does that is because if it holds it far away from equilibrium, then it can have an effect on that delta G and make a reaction that might normally be unfavorable, it can actually force it to be favorable, okay? Again, we're going to look more into this, but that's why we're talking about these things. Okay. Oh, okay. So remember we said that this negative delta G not prime over here that's transformed, it's a constant. Like we said, we can look it up in a book. It doesn't change, okay? But it is for standard conditions, okay? Now, if we want to talk about existing cell conditions, we need an actual free energy change, okay? And the way we represent that is delta G. Oops, sorry. Okay. So delta G is our actual free energy change. Okay. So this gives us an idea of existing cell conditions. They're most likely not standard. Okay. So the actual free energy is going to take into account actual cell concentrations and temperatures. Okay. You can't look this up in a book. It's not a constant. Okay. And so we can relate delta G to our standard transform delta G with this equation. And again, you guys have seen stuff like this before. Do you guys remember what Q is? So
Like
go
the
ahead.
equilibrium taken at any point of the reaction, or
Right.
I'm sorry, like the ratio of reactants and products or something like that.
Yes, exactly. If we look back at our definition of KEQ here, right here, these are the concentrations at equilibrium. Okay, let me write that in. These are all at equilibrium. Okay. When we are looking at Q is also, it's called the mass action ratio. Okay. But these are the concentrations at any point. They're actually what they are. They're not necessarily, they're not at equilibrium. Okay. Oops. Okay.
Professor Laura's,
Yes.
what do the subscripts mean in that equation?
You mean like these little A's and little B's?
Yeah.
Those are the coefficients, the molar coefficients. So, you know, like if you have a reaction like this. Oops. So this is just a generic way of writing something. But if I want to write like 2 waters, you know, plus 6, you know, carbon dioxide or something, you know, something like that, then yeah, the A's, like the little numbers represent these molar coefficients.
Okay, thank you.
Yeah, no problem. Glad you asked. Okay. Okay, so again, Q is at what the actual concentrations are. They're not necessarily at equilibrium. Okay. So this delta G, oops, delta G is going to determine the spontaneity of a reaction. Yes. No. Okay. And it's not going to necessarily be that standard transformed one, but it's still going to help us understand kind of if a reaction, you know, tends to be spontaneous or not. Okay. Now, again, listen, remember what we talked about the natural log. Okay. So this is why a reaction might want to hold, why a cell might want to hold, you know, certain reactants and products far from their equilibrium concentrations. Okay. It's because of this relationship. Okay. So one of your questions on your group assignment is, when will the actual delta G be negative? Okay. So I want you guys to think about one of your, in your group assignment today, something you're thinking about is, when will the actual delta G be negative, right? If this is positive, if the standard free energy, if this is positive, how can we get this to be negative? Sorry, I'm writing a lot here. Okay. How can we get that to be negative? Okay. Huh?
Catalyst.
Well, that could be one way. I want you guys to think about this Q over here. Okay. I'm going to put you in your small groups again. And I want you guys to think about, I'll put you in your same groups, but think about, how can we get the actual free energy change to be negative if the standard transformed energy is positive, given this relationship? Okay. And again, this is part of your group assignment that's due today. So if you want to type in there to get it done, that's fine. Okay. Questions?
Oh, no.
Okay. All right. Okay. So does anyone want to share what they talked about in their group about how we might get the actual delta G to be negative, even if the standard transformed free energy is positive?
Yeah, our group talked about in order for that to happen, Q must be a negative number, meaning that it had to be a number less than 1, multiplied by RT would hopefully make it a larger negative number than the positive delta G, making the overall reaction negative.
Exactly. Yes. Yes. Thank you. Okay. So basically you're saying if this, hold on, okay, if this term, this RT natural log of Q is negative and bigger than our standard free energy change, then a reaction that might otherwise be unfavorable can become, spontaneous. And so how do we get that to happen, right? Q has to be a number less than 1. How do we get Q to be a number less than 1? That means that there has to be, less products than there are reactants. Okay. So if there's less products than reactants, then Q will be less than 1. Natural log of a number less than 1 is negative. It will be multiplied by R and T. And if that term, hold on. Okay, sorry about that. Okay, so if this is a number that's large and negative, it can outweigh this positive standard delta G, and we can get a reaction that's spontaneous. So we will see this in a lot of our transformations that happen in metabolism, okay? And again, these are all things you've seen before, but now they're being applied to this biological system. Okay, awesome.
Dr. Lawrence?
Yeah.
Could you just briefly summarize what it means for a reaction to be spontaneous again?
Yeah, that's a good idea. That's a good point. So actually something I did want to draw that the way I like to think about these reactions is, I don't know if you've seen them drawn out this way, right? Where we're plotting energy here on the y-axis. And we often call this x-axis the reaction coordinate, which I always thought was weird, but it just basically means as the reaction proceeds, right? And you'll often see these represented something like this, where this is giving you the energy of the reactants, right? And if it's starting here, and then we'll have the energy of our products. If it's lower in energy, we consider this change a negative delta G. Okay, so that would be spontaneous, meaning that the forward reaction to go from reactants to products is favorable, energetically, thermodynamically speaking. Okay, now I will give you, this kind of leads us to my kind of a point, is that so far we have been talking only about thermodynamics. Christian kind of hinted at it before we went into our group assignments. He said something about a catalyst, okay? But that kind of, it falls in another, well, that also has a an effect on reactions. But when we're talking about thermodynamics, we are only concerned with where we start and where we end up. Thermodynamics does not care about this path in between, okay? Thermodynamics doesn't care about that, okay? Kinetics does. Kinetics is where that comes in. And remember, kinetics tells you how fast a reaction is going to occur, okay? So again, thermodynamics, we only care about where we started and where we end up. So you can have something like that's very spontaneous, well, like spontaneous.
Like paper burning?
Yeah, exactly. Like that's a favorable reaction, but it's not just going to happen, right? It's not just going to happen. It needs some activation energy, right? Or again, or a catalyst. Okay. So when we talk about in biochem, we don't really talk so much about catalysts, but we talk about enzymes. Okay. And so enzymes, what they can do, right, is they can lower that activation energy for us. So we have a much smaller hill to climb. So that can be, that's what enzymes can do. Enzymes can lower activation energy. Oh gosh, sorry. Okay. That makes a faster reaction. You know, oh yeah, that's fine. And it also, remember, this is kinetics. Where delta G and looking at where we start with our reactants and products, that is thermodynamics, okay? All right, remember, we can also have the case where, same idea, energy and reaction coordinate, where our reactants start off lower in energy than our products. Okay. And that change in energy, again, we got to look at where did we start? Here's our energy of our reactants, our starting. And here we end up at our products, right? If that's a positive delta G there. And therefore, that's an unfavorable reaction. It's non-spontaneous, but that doesn't mean it's not going to occur, okay? So it's just, we're just describing the thermodynamics of that reaction when we say something like that, like a positive delta G or a negative delta G. So again, one way that we'll see these biological systems make a reaction like the one I just drew, like this one, occur is it will hold the concentration of the products very low in comparison to the concentration of the reactants. Because again, of this relationship up here. All right. Ooh, I know that's a lot of stuff. Questions?
What is it? So the one second, standard transformed constant. What does it mean for that to be high or low?
So that's just those are usually measured under, right, a standard conditions.
Oh, sorry, I didn't mean that. I meant the delta G with the with like the 1 and the 0 or whatever
Okay.
that is.
Yeah, the prime and the not.
Yeah. What does it mean
10?
for that to be high or low? Yeah.
So again, if that is negative, then that's telling you that you have a spontaneous reaction and it wants to proceed in the forward direction if it's negative. If it's positive, then it's, you know, an unfavorable reaction and it wants to proceed in actually the reverse direction. Okay. But it also means that those numbers, whether they're positive or negative, were measured at standard biological conditions. Okay, so let me, right here. So they have these standard biological conditions here where, you know, they had the proton concentration held at a constant, the water concentration, magnesium. It's still 25 degrees Celsius and 1 atm, and everything else is at 1 molar concentration. So a lot of times, like in the figures I'll use in my slides and a lot of the textbooks, they will give you this delta G not prime just as a way to gauge like, oh, does this reaction, you know, so when we look at all the reactions in glycolysis, you'll usually get a delta G not prime for each one to give you an idea if that's like a favorable reaction or not. Okay. But remember, they can't really give you a delta G, an actual free energy change, because the exact concentrations of all the components, reactants, and products is going to vary. And it's not going to be at 25 degrees Celsius. Most living organisms are at 37 degrees Celsius. So these just kind of the standard transformed delta G. So our delta G, not prime, just gives us an idea of what the thermodynamics are under those standard biological conditions.
And then our actual free energy change, it's now we have delta G prime naught. Was that supposed to be not prime? See, it's prime naught.
Oh, did I switch the prime and the naught?
Yeah.
No. So whenever, even if I mix them up,
It doesn't matter.
it doesn't matter. Yeah.
Okay.
It looks like in most of my notes, it's always prime and then not. So it looks like I messed it up. So it looks like it's usually looks like the number 10.
Yeah.
Prime and then not. Yeah. But yeah, either way, even if it's flipped, it doesn't matter. I'm still talking about the standard free energy change at biological conditions.
So Professor Lars, does the change in G prime not take into account that doesn't take into account the concentration of product and reactants, only the LNQ does?
It does, but it's assuming that all the products and all the reactants are at 1 molar concentrations. Unless, again, protons is one of your products or reactants, then that's at 1 × 10⁻⁷ molar, because that's a biological, right? It's around pH 7.
Okay, so that's everything under biological conditions, and then the ln to the q is like actually what it is.
Yes, exactly. It's the actual.
Okay, that's where I'm kind of confused though, because this is happening in the body. Like this is like the equation. So if it's already under biological conditions, why would it be different? I'm saying.
Well, because again, these are biological standard conditions, so they still there's just a defined set of conditions, so that way they can do these in a lab and create a table to give us an idea of which reactions are spontaneous or not. But when you're like under certain conditions, right, in the body, like let's say I'm sitting on my couch and I'm eating ice cream, well then my glucose concentrations are pretty high and they're not getting used up, right? But if I'm running a marathon, right, then my glucose levels are getting depleted, and that's going to change. And so we have these standard set of conditions, so we can just kind of have like a reference point, right? But and what's actually happened in the body, just from like from within an hour, you can imagine how dynamic your body is, and you're going to learn in this class. It's amazing. But conditions are going to what's even more amazing though is like you're going to have a rapid like demand for ATP, and your body responds so quick to it, and it has all these kind of pathways in place to respond, so that even though if suddenly I go from sitting on a couch eating ice cream to running a marathon, it's going to try its best to maintain the level of ATP in the body, or even like glucose in the body, but that's going to set off a series of reactions to try to maintain those levels, right? But they're still going to change. So again, that delta G is just going to depend, right, what's going on. And again, remember guys, we've been talking about thermodynamics, where we're only considering beginning and end of a reaction, not how we got there.
Okay.
Yeah. And remember, how we got there, that pathway is kinetics.
So
okay?
this LNQ is always going to change depending on what state we're in.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
That makes sense.
And that's why you can't just go look it up in a book, right?
I got you.
Okay. So again, something can be spontaneous, right? Meaning the energy of the products is less than the reactants. Again, but we said, but like the reaction occurs very slowly because there's slow kinetics. Okay. And so we talked about that.
Dr. Laura?
Yeah.
So I was just, I don't know, I was just wondering if you could it might be better if I ask this in office hours. So when's
No,
your next
I'm sure
office
people
hours?
will appreciate it. People will
Yeah?
appreciate it. Yeah.
Okay. Well, I was just looking at the delta G prime naught and just the delta G, and like looking at the equations, and I realized that if you just supplant the equation for delta G prime naught into the equation for like where it belongs, and then you just do a little rearranging, you pretty much just end up with like RT times the sum of ln q minus ln k eq.
Yeah.
And
I
so
think that, yeah.
it's pretty much just comparing like, and that kind of makes sense because I guess if you have a, oh man, now I got stuck in my brain.
Sounds like you're having
Anyways.
fun with them though. Yeah.
Yeah. Okay.
But what you can start to see, right, is that I'm sure, like, again, I'm looking at it with a chemist lens, right? There's this mathematical component, and I'm sure maybe, I don't know how the biologists are feeling in the class right now, like, oh my gosh, like I didn't think I needed this for biochem. But you'll see that some people like to look at the reactions this way. I like to look at them this way. It makes sense to me. And as we look at the reactions, we'll see it. But you'll see as we start to look at more of the molecules and the biology in here, there's lots of different ways to look at reactions. Okay. It's just, this is going to help us understand. We'll see why the body is doing certain things. And again, it's usually because it's being ruled by the laws of thermodynamics. And so we can come back to these principles here. Okay.
Yeah. Okay.
So
cool.
the thermodynamics kind of helps us determine kind of which direction the reaction wants to go. And so we'll see, like, most of if you start looking at the reactions in glycolysis, a lot of the enzymes are named, for what the enzyme does. But every once in a while, an enzyme is named for the reverse reaction. And that's because once you removed, once you tried looking at this reaction in a test tube versus in the body, it might go, reverse in a test tube when it's actually going forward in your body. Okay. And so I'll point that out when we get to those. But again, it's the thermodynamics that are going to determine the direction. And usually the kinetics is what determines the rate, right? Like how fast a reaction is going to go. Okay. Just again, I don't have a nice figure for this, but I want you guys to know that delta G's, okay, for a sequential reaction. So like if we look at glycolysis, we can look at one reaction after the other and they're additive, okay? So we are going to look more at this, but it allows us to couple a reaction, okay? So we can take an unspontaneous reaction and put a spontaneous one right after it. And usually that's going to involve ATP, and that's going to help drive a reaction forward. Okay. And then again, I put those little video clips on our Canvas page, so you can check those out, and it talks more about that. KEQs, I don't really use this principle that much, but I have it in my notes, but KEQs are multiplicative. Okay. So I don't really, I don't know how helpful that is, but if you want to know that, they are. Okay. But like I said, a common strategy. So a common strategy, I do want you guys to know. Is that we'll couple hydrolysis using water to break ATP to an unfavorable reaction. Okay, so this hydrolysis of ATP really helps drive unfavorable reactions. Therefore, like, as you guys have probably heard, like ATP is like the currency in our body. We need to produce it. Okay. Again, remember, we cannot drive a reaction by heating it up or increasing the pressure or adding in a nasty solvent. We are living organisms, okay? So we got to use the laws of thermodynamics and kinetics to help us drive a reaction. Okay. Questions?
I do have a question. It doesn't really pertain to like the body system. It kind of just has to
Okay.
do with compound and just kind of delta G. It just has to do with the iron and rust. So that's a state of oxidation. So is that favorable because it wants to do it spontaneously and always happen?
Yes, so that's a spontaneous reaction, right? Iron.
And then that means that like iron ends up like eating itself and has less product, so it weighs less after there's rust on it.
That sounds reasonable. Yeah.
Okay. Yeah, I was just thinking about that. That's
Yeah.
all.
Yeah, so you can imagine, right, as the products are getting as reactants are getting transformed to products, right? What happens, right? There eventually it's going to reach equilibrium, right? And there'll be no net change. All right. I am going to actually stop there. So when we meet next time, I usually do use a lot of slides, but with this topic, I do like to write on this first day here. So when we come back, we'll look at some, ways, some kind of go over some organic chemistry that will be relevant in our conversations, just a little bit. We'll look at some structures. So we'll look at the structure of ATP and get really familiar with that. And let's see. And we'll try to apply, a little bit more this idea of, the thermodynamics driving a reaction. We'll also look at reduction potentials. Woohoo, that's fun. Because again, a lot of this is redox chemistry that we're going to be looking at. So understanding reduction potentials and redox reactions is going to be really important. I like to think of like the body as like, or anything, like if you're charging your phone or you put on a light or any kind of thing you use that requires, power, there's this flow of electrons happening. And it's the same thing in us, right? We require this energy. There's this constant, like we said, this constant transfer of energy in our biosphere. And it's this flow of electrons. And remember, redox is either gaining or losing electrons. So that's going to come up over and over this semester. So we'll talk about some redox chemistry on Monday too. So like I said, today and Monday tend to be pretty dense with material. Maybe people feel the whole semester is, but I feel like just reviewing all these topics pretty quickly. But you've seen them all before, but now you're seeing it all together like in 2 days. Okay, so that's all I have to say for today.
So you want us to finish the rest of the group questions and turn it in?
Yes, so you'll have that prep assignment for Monday, and then you'll have that group assignment. So it's just under what conditions is delta G negative, and then do living organisms disobey the second law of thermodynamics?
Okay.
So yeah, it's the 2 questions you guys talked about today in class.
And Dr. Lars, how long would you like the responses to be for that?
Oh, it could be quick. Again, the group assignments are more meant for you guys to, for you to articulate your own ideas. So think of them as, again, you're taking responsibility for your learning. So that's up to you. If you do it, you get credit. I don't,
Okay.
yeah. So if
you
you have a response, as long as you're not, talking about taking your dog for a walk or something, then if there's a response, you get the points. All right, you guys. So let me see.
Dr. Lars, I just
Yes.
have the superscripts for delta G, like, right? Can I just go over those really quick?
Yeah. So the superscripts for delta G, you said?
Yeah.
Okay. Let me see.
So The prime means that it's biological conditions, right?
Yes.
Whereas
Oh.
the not is standard conditions.
Yes. Yes.
So by standard conditions, everything is 1 molar, right?
Yes.
Okay.
So you probably seen the circle before, to indicate like standard conditions. The new thing might be the prime, so like the dash, right? Or the apostrophe. That just is biological standard conditions.
Okay.
And I don't, like I said, I don't really test you on that. I just want you to be aware of it because you will see that like notation in a lot of figures and in textbooks and stuff.
Okay. And then whenever you combine them, it's like the standard conditions, but not 1 molar, just the standard conditions for that organism.
Right. And so when you combine them, when it's a standard, with the not and the prime, then that is mostly everything is 1 molar except our proton concentration, our water concentration, and our magnesium concentration.
Okay.
Just to make it biologically relevant. Again, you don't have to memorize that, but again, just be aware that it's for biological conditions.
Okay. Just wanted to make sure. Thank you.
No problem. All right. Other questions?
Thank you, Dr. Lars.
No problem. Thank you guys for being here.
Thank you. Thank you. Have a good one.
All right. You too.
Hey, so I just wanted to make sure, when we're looking at the first question of under the conditions is delta G negative. So I put less products than reactants would give us a negative Q while using the using the equation delta G equals the delta G 1 plus RTLNQ. Combined with a spontaneous reaction time, we could have a negative RTLNQ greater than our delta G, giving us a slim but available chance to have a negative delta G. Would that work?
Yeah, that sounds good.
All right.
right.
Thank you. Just wanted to
Yeah,
make sure
no
of that.
problem. Yeah,
All right. Have a great day.
you too. Bye.